Welcome to the AP Physics Workbook tutorial. This is on Unit 10, Mechanical Waves and Sound. The section is 10.J, Standing Waves in a Tube. Here, you're going to consider a pipe that is 3 meters long in a gas where the speed of the sound is 360 meters per second. All right. What you're going to have here is the lowest frequency with the longest wave, and so on and so on. Basically, they're making you go through all the harmonics. Okay. So here are the notes for it. Right. So let's take a look at the notes really quick. So this is for a open tube at both ends. And you will see here that the length is equal to 1/2 the wavelength. The reason why is because, do you see how here a full wavelength would look something like this? Right here, then it goes back up. That would be a full one. So this is half of it. That's how they got half. To solve for L, you multiply 2 to both sides, then you get this. Okay, you get 2 lambda. Okay, that's how you get it. Likewise, here, this is when you have it completely as one wave. So the length here is just the wavelength. Here, you have one wavelength plus a half. So to get the length, you multiply by 2/3. Multiply by 2/3. Okay, that is how they get these. This is the relationship between wavelength and length of tube or string. All right, so we're gonna apply that knowledge to this idea. Okay, this is considered to be the first harmonic, also called the fundamental frequency. So let's just grab that over here. We consider this to be the first harmonic. How would that look like? Well, we know that the first harmonic would look something like this. It's half of a wave. So here in the middle, goes down. Okay, so this is where the wavelength, like we said here, where lambda is equal to 2 of the L. And the reason why is because we say it right here. Okay, because it has 1/2 of a wavelength, because there is a half, because there is only half of one wave in the tube. All right, so this is the longest wave. All right, and to do this, we just plug it in. So we know that the L here equals to 3 meters. All right, so let's just plug that in. So lambda is equal to 2, and this was 3. So lambda was equal to 6 meters. And if we want to know the velocity or the frequency, okay, we know velocity equals the frequency times wavelength, and we know that V was equal to 360 meters per second. So we just plug that in. 360 is equal to 6 frequency times your 6. So divide 6 to both sides, divide 6 to both sides. You get 60 hertz for the frequency. All right, that's it. So this process is going to be repeated over for this one. So the second, this is called the second harmonic. All right. And for the second harmonic, we know that lambda is just equal to L, because there is one complete. I can write it here because there is one complete wave. Okay, this is the second harmonic. So if one full wave would look like this, and this is a cosine. Whoop, yep. Right, yeah, that's So that's horrible. So that's better. That's a cosine wave, right? It shouldn't go out of the tube. I try to draw it the best I can. Okay, and the other end would look like this. Okay, try to draw it the best I can. All right, so here lambda just is equal to 3 meters. And if you want to know, the frequency, okay, and this is also considered to be the second harmonic. All right, and if you want to know the velocity, you just plug it in. So 300 and so you have 360 is equal to frequency. The lambda here is 3, so divide 3 to both sides. You get 120 hertz as the frequency here. All right, and the last one, this is the third frequency. The third frequency is going to be called the third harmonic, and we have it right here. All right, okay, and boom, boom, boom. And the way we explain this is because in the tube there is going to be a 1.5, so 3/2, right? So there's going to be 1. So here's 1 complete 1, then a half, right? So imagine this as 1, and this is the other half. Do you see? Hopefully you see it. All right. So I just made that dash just for you to see where the 3/2 comes from. All right. And we know that is called the third harmonic. And if we multiply to solve for the wavelength, we get this. The wavelength is equal to 2/3 the length. All right. So let's plug it in. So lambda is going to be equal to 2/3. And we know the L here was equal to 3. Okay, 2/3 L times 3. Okay. All right. So you're not gonna like this explanation, but this lambda here is actually now going to be the new lambda for the third harmonic is going to be 1.5 meters. Okay, so as you go from the first harmonic to the second to the third, the wavelength is basically keeps breaking down smaller and smaller. Okay, then if you want to know the velocity, so frequency times lambda, that just is 360 is equal to frequency lambda is 1/5. So 360 divided by 1/5. Okay, give me a second. Oh, okay. So there is an error. I'm sorry. Okay, so this was wrong. My original calculation was correct. Okay, because I just checked it. Because this is the way. Watch, I checked my own mistake. So this is 60 hertz. This is 60 hertz. The answer here has to be 180 hertz as the frequency, because as it goes, you're adding 60 hertz each time. Okay, now if I go back here, let me show you the calculation. Lambda is equal to 2/3. L was here, was 3, right? This cancels, so this should be 2 meters, right? So this is 2 meters. Now all you have to do is plugging a 2 here, then divide, right? So because the wavelength is 2 meters, so divide by 2, that gets you 100 hertz for the frequency. There you go. Okay, right? I had to double check my work. Okay, so this makes sense. It goes from 6, 3 to 2 meters. Yeah, okay, because the frequency should be adding. Perfect. Next, this is when the pipe is closed at one end. So here you can still grab these notes here to help you, right? Because again, these needs to be memorized if you want to understand. But this time in this example, it is closed on the right. This is closed to the left, so it's opposite to this. Okay, because it says here it's closed to the left side, right? So the left side is where it's starting here. So, right, it's gonna be half again. Oh, here it's gonna be half like that. Well, so the wave, it's supposed to be like this, right? Should go up. Then you see how, right? Then it's going to go down like that. Okay. But it's like that. Okay. It's half of that, right? Then likewise, okay. There's that one as well. You could also start down there. Okay. All right. So here we saw that this is the first harmonic for the closed pipe. And it is defined by this. L is equal to 1/2 lambda. Okay. And to solve for it, we just multiply 4 to both sides. So you get 4 times the length is equal to lambda. And we know the length was equal to 3 meters. So 4 times 3 is equal to lambda. So this is 12 meters for lambda. All right. And if you want to know the velocity, it is frequency times lambda. We know that the velocity was equal to 360 meters per second. That was what the problem gave us. Okay. And then we have 360 equals to 1 frequency times 12. So divide 12 to both sides. You get here 360 divided by 12 will get you 30 hertz. Right? So the first harmonic for the closed pipe is actually half of the open pipe. Right? That makes sense because one end is closed. So it's going to be half of that. Right? So the next harmonic looks like that. So looks like it's a complete, almost a complete wave. It's 3/4 of a complete wave. Okay, so that's gonna be hard to draw. Up, down, then this way. Okay, or you can start like this. Right, these are the two ways. Right, so this is actually called the third harmonic. Okay. So for the open pipe, it goes by odds, right? So here you have 3/4 of a complete wavelength. So just, okay, if you multiply 3 over, if you want to solve for the wavelength, you have 3/4. No, so you would multiply by right here. You would multiply by 4/3 to both sides. So you get 4/3 length equals to lambda. Okay, so 4/3 over 3 times 3 for the length equals wavelength. So lambda is equal to 4 meters here. Want to know what the frequency is? 360 for the velocity. Frequency lambda was 4. Divide 4 to both sides. You get 90 hertz. Okay. Why? Because technically there is a middle step here. So there is a second harmonic, right? And in the second harmonic, what is happening is that this is going to go to the second harmonic by adding 30 hertz. Okay? So the second harmonic, so here, let me show you. It's going to add 30 hertz here, right? So the second harmonic would have been at 60 hertz. Then to go to the third, you add another 30 hertz. See, you see how you got 90? If we continue the pattern here, we're gonna add 30. So we're gonna add 30 to the fourth harmonic here, and this is gonna get you 30. 9, 10, 11, 12. So this is 12 hertz. Then to go to the fifth harmonic, you're adding an other 30 hertz. So getting you 150 hertz, right? You're going to see how this answer came to be when we actually do the problem, right? So let's do the problem. The fifth harmonic is defined by this. All right, it has one complete length plus 1/4. Okay, so this is your complete one. So 1, then a 4th. All right, oh, that's your 1, and this is your 4th. Okay, so this is multiply 4/5 to the other side. So 4/5 length equals to lambda. So plug it in. This was 3 equals to lambda. So 4 divided by 5 times 3 gets you, this is 12/5 meters equals to lambda, or you can write it as 2.4 meters for lambda, however you want to do it. So 360 is equal to, so velocity equals frequency lambda. Frequency was 2.4 and the lambda was 2. So lambda was 2.4. Divide 2.4 to both sides. So frequency here, right, it should be that 360 divided by 2.4. Perfect, 150. Right? There you go, hertz. That's how you do it. Okay, let's see, is there anything else? All right, so do you see how it kept going by 30 hertz each harmonic? But this is for the closed pipe on one end. Please understand, it jumps harmonics for the frequencies. Okay, all right. So here on the number line, draw an open circle at each end of the pipe you found in part A. Then use the pattern to get more open pipe frequencies. Well, we already know that. Okay, so let's just, do you see how you add 30 hertz to each side? So the next one, okay, you're going to add another 60 hertz. Okay, so that becomes 240 hertz. Then you're going to add, what are we adding here? 60 hertz, yeah, each time. So we're adding 60 hertz each time. So that becomes 300 hertz. Then to the next one, you add another 60 hertz. So that should be 360 hertz. Okay. Likewise, I think the next one here, remember you want every single 2. So the 6, so the 6th harmonic should have 180. So the 7th harmonic should have 210. Right? Do you see how it goes up 30 hertz each time? Okay. But here, the next one that we're going to write is the 7th harmonic. So we want the 7th here. Okay. So this is 210. Remember, this is the 7th harmonic. Okay. This is going to be the 9th harmonic. So it's going to be 270. And this is going to be the 11th harmonic. So it's going to be 330. Okay. There you go.